Okay, as the last part of this tutorial, we're going to show some post-processing for the results. So the simulation continued for 4,000 time steps, and then the simulation converged. So if you want to take a look at the residuals, so we have the residuals in the monitors, and then we can plot them. So we see that the residuals have all dropped to below 10 to the power of minus 9. So the simulation has converged. Now we can take a look at the flow, for example. So here we have the results, and then we have the graphics, and we can do some contours. So the velocity magnitude. So let's take a look at the velocity magnitude. Okay. So this is the whole domain. So now we can zoom in towards the duct. Okay, so we have the duct region, the nozzle, the throat, and the diffuser. So we see that we have some low speed regions. So if we change to axial flow, and then we can see that so the dark blue regions are negative velocity, so we have some rotational flow here, reverse flow here, and then we have some acceleration of flow here. So here the velocity, if you right click, you can see that it's almost 4.7 to 5.4, but in this region we have much higher velocity, so the acceleration of the flow. So this is what the convergent-divergent duct is supposed to do, so that it accelerates the flow, so the turbine is located here and benefits from the higher velocity. We can also check the pressure, static pressure, or let's take a look at the pressure coefficient. So we see that we have lower pressure here due to the acceleration of flow. Let's also take a look at the vectors, the vector field colored by the axial flow. Okay, now we have the vector field. So already here you can see that we have a recirculation region with acceleration of flow. So we can skip some of the vectors. So I put 5, and then I display again. So some of the vectors are skipped, and then I think we need to skip a bit more, because in this region especially we have a lot of vectors. So I skip 10. So still in this region it's not clear because of the large number of vectors that we have. So we can try without auto scaling. This is not righteous. I would go for the normal arrows instead of 3D arrows. Yes, this makes it a bit clearer. You can also do different other types of arrows, but what I wanted to actually show you is the reverse flow region here that you can see. So if you go out, so this is the duct, and outside we have a reverse flow region, and then we have accelerated flow here. So already also by the velocity vectors you can also get some more understanding of the flow. You can do more, you can do also plots. So let's do, for example, XY plots, and then we can plot the pressure coefficient along the axis. So here is the region where the duct is located, so you have a high pressure drop. And then if you look at the axial velocity, then you see that we have the acceleration of flow. So we can a bit limit the axis. So for example, for the x-axis, If we remember, the duct goes from minus 1 to, so we had half a meter for the nozzle, half a meter for the throat, and also I think 2 meters for the diffuser. So I think if we put 1 minus 1 to 5, we will be in the region of the, yes, in the region where the duct is located. So here we can better see the acceleration of flow from 5 to 10. So we have an amplification factor of almost 2. So this is also another way to take a look at the flow. Here we can also, if you want to check, for example, the amplification factor, which is the velocity acceleration with respect to the free stream velocity, we can create a simple equation here using the custom field equation, and then you can select the axial velocity and then divide it by 5, which is the free stream velocity, and I name it amplification factor. We define it, and now we already have it here, and then we can this time plot this on the axis. So we can see that the amplification factor goes to almost 2. We can also plot the pressure coefficient along the duct wall. So you should note that this is both the inner and outer wall of the duct. So you should distinguish between them, or you can, from the beginning, you can define them with a different name when you define the boundary condition, so that here you have the wall, inner wall and outer wall, and you can you can plot them separately. So, but what is apparent to us is that in the inner wall we had acceleration of flow, and then we expect that in this region where we have acceleration of flow, we should have pressure drop, and then probably this should be the inner wall and this should be the outer wall. Okay, so we took a look at the XY plot, we took a look at the contours, and we took a look at the residuals. Here we can also plot the grid. So this was all for the very simple post-processing in Ansys Fluent. Now we're going to see the summary of what we learned during this tutorial lecture. We learned how to prepare all the steps to simulate the flow of around a convergent-divergent duct, which is typically used to accelerate the flow for wind energy harvesting purposes. So the steps included creating a geometry of a duct using Ansys Design Modeler, decomposing the domain to facilitate the grid generation, generating a hybrid grid with bound layer grid along the duct walls using Ansys meshing, prepare the simulation settings in Ansys Fluent, and do preliminary post-processing in Ansys Fluent. And everything was arranged within the Ansys workbench environment. Okay, this was the first step. Now you're ready to go with your own simulation for wind energy purposes.